This is an intro to the Fundamental Theorem of Calculus, Part 2. In this video, I'll go over what Part 2 of the Fundamental Theorem of Calculus is and how you can use it to solve calculus-related questions. And so Part 2 of this theorem relates to derivatives and integrals and how both of them relate to each other. And so what Part 2 states is that when an integral is provided to you, usually by a question, with bounds that include x in it. So if the upper bound has x in it, you can use the second part of this theorem. And so if an integral is given to you and x is the upper bound, you can use this theorem. And so what the theorem states is the derivative of an integral is the original equation. And so what I mean by that is that when you want the derivative of this function that's given to you, you would just try to find the original equation, because in this case f prime of x will equal the original function, lowercase f of x. And so this is assuming that the original equation is lowercase f of x. So if you find the derivative of an integral, you'll get the original equation. And this basically states that integrals and derivatives are inverse functions. So that's why this theorem works. And so how do we solve this now that we know what the theorem is? To solve this, all we need to do is replace the variable inside the integral with the upper bound. So in this case, we can replace t with x. So x cubed plus 1. And we multiply this by the derivative of the upper bound. So in this case, the derivative of x is just 1. And so this is uppercase f prime of x, which is also equal to the original function lowercase f of x. And so in this question, we have the equation sine of t dt from 0 to x squared. And so since you have an integral with the upper bound that has a variable of x, we can use the second part of the Fundamental Theorem of Calculus. And so to find the derivative of this integral, we simply need to replace the variable inside the integral, which is t in this case, with the upper bound. So we replace t with x squared. And don't forget, we multiply what we get by the derivative of the upper bound. So in this case, the derivative of x squared is 2x using the power rule. And so this is our uppercase g prime of x, which is also equal to lowercase g of x, assuming that lowercase g of x is the original function. So pretty similar, we do the same thing. We have an integral, and it's asking us to find the derivative of this integral. And so to find the derivative of the integral, we just need to find the original function. So replace the variable with the upper bound. In this case, the upper bound is ln of x, natural log of x, and we can replace that with natural log of x. And now we need to multiply by the derivative of the upper bound. So the derivative of the upper bound, natural log of x, is just 1 over x. So you can write this as e to the power of ln of x squared divided by x. So that's equal to h prime of x, which is the derivative of h of x. That's also the original lowercase h of x function. And so there are different ways of asking the same thing. Previously, we were asked to find the derivative. In this case, the question simply asks us to determine the value of this d dx. And so all of them basically mean the same thing, finding the derivative of this integral. And so all we need to do is use the part 2 of the theorem. Cosine, replace t with upper bound x square, and multiply this by the derivative of the upper bound, which in this case is 1. So that is the derivative. So in this question we have evaluate the derivative of square root of 1 plus t squared from x squared to 3x. So if you notice in this question, not only the upper bound but the lower bound also has the variable x. And so you need to keep in mind that when both the bounds have x in it, there's a special rule that you must understand, the Leibniz rule or the Leibniz rule. And so this rule states that whenever x is in both the lower and upper bound, we simply start by replacing the upper bound. So in this case, we replace t with the upper bound 3x squared, and then multiply this by the derivative of the upper bound, which is 3 in this case, using the power rule. And we subtract this by the same thing except with the lower bound. So in this case, we would replace t with the lower bound. So in this case, it will be 1 plus t. If you replace t with x squared, you get x squared. And so using our law of exponents, we know that x squared to the square is equal to x to the power of 4. And that multiplied by the derivative of the lower bound, which is in this case 2x. And so this is basically what you would do if you had a variable x in both the upper and lower bound. Now when you have a variable x in only the upper bound, you would simply use this, the first part of this rule, which is this part over here. And that's only when the lower bound is a constant. So again, in this question, we have 2x in the upper bound and x for the lower bound. And so we know that we need to use Leibniz rule, which is basically replacing and doing how we'd normally do for the first part. So we'd get 1 plus 2x over 1 plus 2x squared times the derivative of 2x, which is 2. Subtract this. Now, second part, it's new. Subtract this by natural log of 1 plus x over 1 plus x squared. Multiply this, multiply this by the derivative of the lower bound, which is 1 in this case. So this is our answer. Now we can simplify this, but for right now I think I'll leave it as is. So again, we have e to the power of x for our upper bound and cosine of x for our lower bound. So we know we have to use Leibniz rule. And so to find the derivative, we use Leibniz rule. So replace sine t with e to the power of x over 1 plus e to the power of x to the power of 3. We can write this as e to the power of 3x, since using a law of exponents, we know that e to the power of x to the power of 3 is also equal to e to the power of 3x. But I'm going to leave it like this for now. And we multiply this by the derivative of e to the power of x, which is a rule, and that is e to the power of x is just e to the power of x when you take the derivative. Now, since we have a lower bound, which is into constant, we subtract this by replacing the t with the lower bound. We get this over 1 plus cosine of x cubed. And we multiply this by the derivative of the lower bound. So the derivative of cosine of x is negative sine x. Negative sine x. And again, you can simplify this, but for right now, I'm going to leave it as is. Of course, you can simplify here and then multiply through, and then simplify here, multiply through. But yeah, this should be okay for most exams. So, last question. Find the value of h prime of x given h of x. So again, in this case, we have a constant for the lower bound, so we don't need to use Leibniz rule. And all we need to do is substitute t with the upper bound, which is x. 1 plus x squared. Multiply this by the derivative of x, which is 1. So this is h prime of x. And so this is basically what the second part of the fundamental theorem of calculus is. When you have to find the derivative of an integral, it's basically finding the original function, because the integral is essentially an antiderivative, meaning an integral and a derivative are simply inverses of each other.